Gradient of a scalar field, as you can see here, it is in Cartesian coordinates or the what we call as rectangular coordinates. Generally, uh, when we say the coordinates are x comma y comma z, or you can also call it as x1 comma x2 comma x3. So when it is x comma y comma z, so you can write the gradient of a scalar field like this. When x1, x2, x3 are the coordinates what you represent, then you write the gradient like this. See, what is the notion here? See, del S means generally what is del? Delta 1 tau by tau x. I should say uh, says delta x if possible. Plus or as per the textbook says delta 1 x1 delta 2 x2 like that also we can say. I can actually refer like this. So delta 1 tau by tau x1, delta 2 tau by tau x2. Next, plus delta 3 tau by tau x3. So this is del operator definition. So multiplied scalar quantity. Scalar quantity, now it is just you know, represented like this, tau x1 plus delta 2 tau s by tau x2 plus delta 3 tau s by tau x3. So this is our, so little more, discussion. Now let us take the divergence of a vector field. Divergence of a vector field. So that is delta dot again a vector. So this the result should be also a vector. Generally, del operator, as we have seen now, can also write in a general notation like this. Earlier we have seen the delta notation like this. Now I delta I tau by tau xi. Please, I request all to refer the standard books also. There is no issue. Now the v vector, generally any vector is written in terms of its components in x direction, y direction, z direction, or 1, 2, 3 direction. So this can also be written, but let us not stick to I because I is already used. Let's say this is j. So this is written with respect to unit vectors and its component j. That means j can take values from 1, 2, 3. J I can take values 1, 2, 3. So this is the two separate definitions of a vectors. So this divergence you can write in this way. So this is like this. Sigma I, sorry, it is not conical delta I tau by tau xi. So this is one particular component. So let us actually write like this. Dot sigma j delta j, and then you can write this as j. This is the product. by definition actually. Now it is a dot product, so we can write this way: sigma I sigma j delta I dot delta j like this, and then you are left with dou by dou xi, dou xi, and vg. Now the basic definition also comes in the picture. So you see, we are working on, I think you are able to understand divergence of a vector field. See, dot i del dot I cross del dot j, dot product of the two Kronecker delta operations. What it because these things are important. If this is not remembered, we will be in little trouble. So by definition also they are proved while discussing the Kronecker delta. So you need to actually understand the what you call the output of these two. So this is very simple. A scalar delta ij. So these two are the vectors. These two, this one and this one are the vectors. So you are coming a scalar quantity. So how you write this? I j. Now this becomes a scalar delta ij tau by tau x I bj. I think to this point, I hope I am clear to you, better understand what how they are being written, which can be applied to any type of vector. This is now how it can be written. See, now I make it like this: sigma I dou by dou xi. Okay, and then I write sigma j delta ij vj. This can be written this way also because this is only I, but the sigma is worth it with this also, right? But as a whole, this particular total quantity, what is written, can be written in a compact form, which is here. Now, simple VI. What is VI? Actually, what is vector V? What is a vector V? Delta. No, you can actually write like this, right? So just imagine and then visualize the concept here actually. So like this, if I can mention here, so this will happen like this. Okay. See, me writing here, instead of writing this like this, yeah, we can write like this, sigma I say, yeah, correct. There is nothing wrong here. Okay. Right. You can actually look into this way the picture and then proceed. But here, dou by dou x, see, epsilon Kronecker delta, this portion, which is not repeating the indices, which is not repeating this I, so this can be written as Vi instead of sigma j delta I j bj. This is from Einstein summation principle. Okay. Let us take one small example of delta curve, right? So this is Uh, Let me take a small example. Delta 1 dou by dou x1 plus delta 2 dou by dou x2 plus delta 3 dou by dou x3 dot, let us take on b1 delta 1 plus b2 delta 2 plus b3 delta 3. Their deltas are input. So a dot product, generally a dot product is there. So directly you can do like this. That means delta 1 dot delta 1 dou by dou x1 b1 plus. So that means this quantity and this quantity. Now the second quantity and the second quantity. What will happen to that? Delta 2 dot delta 2. This becomes dou by dou x2 v2. Yeah. Now v2 is a scalar. Okay. V2 is a scalar. Plus dou 3 dou 3 dot dou 3, and this becomes, sorry, delta by, and dou x dou by dou x3 v3. So this is a, that means, those who are in confusion, suppose if I have 2 I cap plus 3 j cap plus 4 k cap dot product of 6 I cap plus 2 j cap plus 7 j cap. So what will happen is this one multiplied by this. So what will happen? 2 into, sorry, 2 into 6 into I cap dot I cap. Whereas the scalar product of itself is 1. So likewise, 3 into 2 plus 4 into 7. So answer will be scalar. This is for your understanding only. Nothing to brood over too much. Okay. Chalo. Now what will happen to this place? 1. So dou by dou x1 v1, dou by dou x2 v2, dou by dou x3 v3. So this is our quantity. As it is, if I take the delta product, now you can see what we have obtained here. See what we have obtained here. So I can write this as, I can write this as sigma I dou by dou xi here. So this is what it is being proved.